Welcome, students, to General Science 101. I'm your professor. What we are going to do today is we are going to continue on from where we left off last time. Last time we explained what is the difference between temperature and heat. We stated that temperature is the degree of hotness of an object and heat is the amount of energy that object possesses. Looking at these two differences, we said that in order to find out what is the heat energy prevalent in a body, or how much heat energy a body possesses, we need to know its temperature, and B, we need to know the temperature of the object to which it is going to lose that heat. Heat, being an energy, has to flow from a higher level to a lower level, and in order to find the temperature, we first said that we require a property of a material which changes uniquely with temperature, so that its temperature increases, the property has to either increase or decrease. And we then said that the ideal form, which we normally use in practical thermometers, is a liquid and glass thermometer. In a liquid and glass thermometer, what we had was, we had a bulb which contained some liquid, which was forced to move up in a very thin capillary tube. Because the capillary tube had a very thin cross-section, then we could assume that the expansion or the movement in this capillary of that liquid would be proportional to temperature. It should be almost linear, and we considered that as a one-directional expansion. We then further stated that in order for the thermometer to work, we required some reference points known as fixed points. And for a practical thermometer, we said the two fixed points were the ice point and the steam point. The ice point at normal temperature and pressure is when you have got a mixture of ice and water kept for a certain amount of time so that the thermal equilibrium is attained. And when you add the thermometer to that mixture, you are going to get the temperature which refers to the ice point, which is 0 degrees Celsius. It is also 273 degrees Kelvin on a Kelvin scale, and you can say it is 32 degrees on the minus 32 degrees on the Fahrenheit scale. So we then looked at the different scales. We said if it is 0 degrees Celsius, it should be equal to 273 Kelvin, and it should be equal to 32 degrees on the Fahrenheit scale. And all three scales should agree at that point, because we are giving this point by definition. By definition, we said ice point corresponds to 0 degrees Celsius, it corresponds to 273 degrees Kelvin, and it also corresponds to 32 degrees on the Fahrenheit scale. Then we took the same thermometer and placed it above boiling water, and the thermometer is placed in steam. In other words, it is above the level of the water. It is not dipped in the water. Why it is not dipped in the water? Because the water contains bubbles which are coming up, and you might have different temperature gradients there, which might give you an erroneous reading. And however, because it is known as a steam point, the temperature of steam, that is the vapor which is rising above boiling water, has got to have a fixed temperature, which is 100 degrees Celsius. Why are these fixed points is something which we are going to be discussing today. Then we looked at the parameters of a liquid and glass thermometers, and we said, okay, these are the parameters. This is the lower fixed point, which is the ice point. This is the upper fixed point, which is the steam point. Dividing this by 100 equal divisions, because we are assuming that the liquid in the glass thermometer is expandingly uniform with temperature, and therefore with a 1 degree rise, the level of the liquid should rise 1/100th of the length between 0 Celsius and 100 Celsius. Now, if it was a Fahrenheit scale, it would be from 32 degrees to 212 degrees Fahrenheit, and if it was Kelvin scale, it should be from 273 to 373 degrees Kelvin, and we would have a 100 degree Kelvin gap between the ice point and the steam point, and we should have a 100 degree difference between the ice point and the steam point for the Celsius. However, in the case of Fahrenheit, we have a 180 degrees difference between the ice point and the steam point. In order to convert the temperature on one scale to another scale, we use a relationship where we have the temperature on one scale minus the temperature at the ice point on that scale divided by the number of divisions on that scale, and this should be equal to the temperature on scale B or the other scale minus the ice point on this scale divided by the number of divisions on this scale. Now, For example, if we are going to convert from Celsius to Fahrenheit, it would be temperature in Celsius minus temperature at the ice point, which is 0, divided by number of divisions on that scale, which is 100. So Tx minus 0 divided by 100 should be equal to the temperature in Fahrenheit, Tf, minus the ice point, which is 32 degrees. So Tf minus 32 divided by 180, giving, and what we did was, in the formulation, we came to a relationship that Tc is equal to C over 5 is equal to F minus 32 over 9, and we can rearrange it in any way we form. In order to reinforce what we have done, going from one scale to another scale, let's look at a couple of numericals, and that is what we are going to be starting today. Let us look at the examples of something two extremes. The hottest place on Earth, that is the planet we live in, has been recorded as 70.7 degrees Celsius, and this is in a desert in Iran. It is a particular place which is known as abiotic. By abiotic we mean this does not have life in it. It does not have life to the extent that even bacteria has not been discovered in this place. It's in the Lut Desert in central of Iran. The temperature there recorded in 2005 was 70.7 degrees. This is the hottest temperature, whereas when you look at the coldest temperature, natural temperature on Earth, was recorded at the South Pole in Antarctica. At the Russian station Vostok, the temperature was recorded on 21st of July 1983, and it was minus 89.2 Celsius. Now let us take these two temperatures, put them in the formula which we developed last time, that is Tc is equal to 5 by 9 multiplied by Tf minus 32, and Tf is equal to 9 by 5 Tc plus 32, and let's see what is the Fahrenheit equivalent of these temperatures. For the hot temperature, of course, we will get 9 divided by 5 into 70.7 plus 32, giving you a temperature of 159.3 degrees Fahrenheit. 159 degrees is very, very hot. In fact, so hot that living organisms more or less just cannot survive there, and you need special protection if you want to go out in that place. Similarly, when we look at the other extreme, Tf cold, then it will be again 9 into 5 multiplied by minus 89.2, because we put this minus sign there because we know it is a minus, it is below 0, so the minus remains there, plus 32, giving us Fahrenheit temperature of minus 128.6 degrees Fahrenheit. Again, another extreme, again an abiotic region where living organisms would rather not survive. They would be just frozen or in hibernation. Let's look at another example when we are going to change these same values into Kelvin scale. Now, for the Kelvin scale, the relationship is the temperature in Celsius should be equal to the temperature in Kelvin minus 273 degrees, or temperature in Kelvin should be equal to the temperature in Celsius plus 273 degrees, because the 0 degrees of Celsius scale corresponds to 273 degrees on the Kelvin scale. So the hot temperature would be 70.7 plus 273, giving you a temperature of something like 343.7 Kelvin. Whereas for the temperature of cold temperature, the temperature in Kelvin cold would be minus 89.2 plus 273 would give us about 183.8 degrees Kelvin, which is more or less near about the freezing point of oxygen. Now, let's do another numerical. Let's find a temperature on which the Celsius scale and the Fahrenheit scale correspond. Now, the only information which we are given in this question is that the Fahrenheit temperature and the Celsius temperature are the same. We are not given what temperature it is. So basically, it is just setting up the equation, putting in the values, and trying to get it. The equation we will have is the basic equation Tc minus 0, that is temperature in Celsius, minus the ice point in Celsius, which is 0 degrees, divided by number of divisions of the Celsius scale, which was 100 divisions. This has to be equal to temperature in Fahrenheit minus 32 degrees, because that was at that point, divided by 180. Now, when you solve it, basically you get Tc is equal to 5 over 9 into Tf minus 32. However, we have been given the information that temperature in Celsius and temperature in Fahrenheit are equal. So we replace Tf by Tc, and we get 9 Tc is equal to 5 Tc minus 32 multiplied by 5, or 4 temperature Celsius is equal to minus 160. So temperature in Celsius should be equal to minus 40 degrees Celsius. Minus 40 degrees Celsius is temperature at which both scales would have the same reading. It does not mean that both scales are recording the same temperature. The temperature on minus 40 degrees F would be something different. In fact, minus 40 degrees Celsius would be on minus 40 degrees F. So both temperature scales would be giving us the same temperature. They agree at 0 degrees. At 0 degrees Celsius, this is 0 Celsius and plus 32. However, at minus 40 degrees Celsius, the thermometer of the Fahrenheit will also record minus 40 degrees Fahrenheit. Hopefully, these two things reinforced what we did it. So when we are looking at temperature scales, we have to know that temperature scales require the following things. A, it requires a substance which has a physical property which changes continuously between temperatures, or as temperature increases, the increase should be continuous. It does not necessarily mean it has to be proportional, because with the advent of modern electronics, we can always devise systems in which we have a huge number of points pre-fed into a microprocessor. So any value which is given by that property can be translated and we can get a digital readout. We also require fixed points. In other words, for practical purposes, we require the ice point and the steam point and the number of divisions between them. The practical scales, of course, are the Celsius scale and the Fahrenheit scale, which require 2 fixed points in both of them, that is the ice point and the steam point. However, when we go to the absolute scale or the Kelvin scale, it requires only 1 fixed point. The reason it requires a 1 fixed point is that the other fixed point is absolute zero. And we are going to be discussing absolute zero today. So we will discuss that as we reach that point. And Kelvin scale, the Kelvin is the SI unit of temperature. What we are going to try and explain and discuss today is A, we are going to be looking at thermal expansion. When you provide energy to some object, some material, normally it is going to expand. And it is true for all solids, liquids, and gases. We are also going to discuss certain aspects which are known as anomalous. Anomalous means that it does not go with the norm. All materials expand when heated. However, there are some materials which do not expand when they're heated, or rather they contract. And we are going to be discussing one of these one cases. We are also going to be looking at the Boyle's law and the Charles law. In other words, we are going to be looking at the laws which govern thermal expansion in gases. Now, when we say we are looking at thermal expansion, we are looking at expansion of matter. Now, when you heat matter, it undergoes physical expansion, and this expansion is what we term as thermal expansion. And when you heat either a solid, a liquid, or a gas, they all expand. However, as a rule, solids expand a little bit amount, liquids and gases expand with a larger rate, liquids expanding more than solids, and gases, of course, expanding more than solids and liquids. Now, different materials will change differently. In other words, the rate at which materials will expand will be different for different materials. And if you have two different materials, one might expand a little amount, the other might expand a larger amount. And we use that in practical applications. The most common application is a thermostat. A thermostat is a very common instrument which is used in domestic appliances. It is used in your water heaters, in your geysers, it is used in your electric irons, and it is quite a common thing. Now, how does it work? What we are going to be looking at is a mechanical thermostat, not an electrical thermostat. A mechanical thermostat is basically 2 strips of different metals. Let us say this is iron and this is brass. They are welded together so as to form one strip. Now, when the strip is heated, the iron, which has a lower value of expansion for a given range of temperature, it is going to expand less. However, brass, because it expands more, is going to expand more. So when the outer side is going to expand more, it is going to bend this into a particular direction. And because of this bending, this strip has the capacity to exert a force. This force which is exerted is then used to make or break an electrical contact. In case of your water heaters, your geysers, it makes or breaks a mechanical contact. It just shuts off the gas which is going towards the burner. suggests the pilot remains ignited. However, the main gas supply is shut off, and you are then go into a dormant mode, and the temperature is maintained. However, in case of an electric iron, or in cases of other your air conditioners, for example, then these strips just make or break an electrical contact, and when the electric contact is broken, either the heater starts on or the air conditioner switches off, depending upon what mode it is, whether the air conditioner has to switch on contact or which it has to switch off on contact. It depends upon the engineer or the requirements. However, that is where they are used. Now, the expansion which we are going to be looking today, we are going to be looking at the two types of expansion. We're going to be starting with linear expansion. When we say something expanding linearly, we say it is expanding in one direction. Now, normally a student will ask a question. Materials have three dimensions. They have length, they have breadth, and they have height. So how can we say that material is expanding only in one direction? What will happen to the height and the breadth? Don't we consider that? The answer to that is that if we take a very thin rod, a long rod, let's say about 50 centimeter rod is taken, which has got a diameter of about 1 centimeter squared, so 1 centimeter and 50 centimeters long. Now, if you heat it and it expands by 1 centimeter, then its thickness is going to increase in the same ratio. So 1 over 50, so 1/50th of a centimeter is what is going to increase, about half of a millimeter, which we can consider to be negligible for our purposes. And for our practical purposes, we say this is now constrained to expand in one direction only. For practically, we do not use a 1 centimeter squared iron rod. We use something which is about a 1 millimeter, so that reducing this volumetric expansion even further. Now, when we look at a rod, on what will its expansion depend? A, it will depend upon the original rod. If the original rod is small, the expansion will be smaller. If it is larger, the expansion, of course, would be a larger amount. It will depend upon the change in temperature. If I heat the rod, let's say, by a 10 degrees Celsius, it is going to expand, let's say, that much. If I heat it by 100 degrees Celsius, it is going to expand by a larger amount. And thirdly, it will depend upon the material of the rod. Like we said, that if iron and brass, when you compare them, iron expands less, brass expands more. Therefore, if the rod is made of brass, it's going to have a larger expansivity, and if the rod is made of iron, it is going to have a smaller expansivity. On the slide which you are going to be seeing right now, I have just depicted it that you have L1 is the length of the original rod, whereas L2 is the length of the rod which has expanded after the temperature has gone up from T1 to T2. So the change in length is what we are looking at. The change in length is going to be the new length, that is L2, minus the original length, which is L1. And let us, when we put this into a relationship, the change in length is going to be proportional to the original length. Like we stated, if it's a smaller rod, the expansion will be smaller. If it's a larger rod, the expansion would, of course, be of a larger amount. Therefore, the change in length, that is L2 minus L1, has to be proportional to the original length, which is L1. We also know that the change in length has to be proportional to the change in temperature. For a larger temperature, you should get a larger expansion. And when we combine these two relationships, we find out that the change in length should be proportional to the product of the original length and the change in temperature, or L2 minus L1 is proportional to L1 delta T. Now, when you convert proportionality into a constant, because it's a linear equation, we would say alpha is the coefficient of linear expansion. L2 minus L1 should be equal to alpha L1 in multiplied by T2 minus T1. Rearranging, we find that L2, which is the increase, has to be equal to alpha L1 multiplied by delta T, or T2 minus T1, minus the original length, plus the original length, because when it goes to the other side of the equation, the minus converts to plus. And from which we get our relationship that L2 is equal to, taking L1 common, L2 is equal to L1 into 1 plus alpha T2 minus T1. Or if you want the value of alpha, then alpha, of course, has to be equal to L2 minus L1 divided by L1 T2 minus T1. Now, what exactly does this mean? Now, if L2 minus L1 is 1 meter and T2 minus T1 is 1 degree, and the original length was 1 meter, for the length to double, that is what the coefficient of linear expansivity is. The linear expansivity is that for a change of 1 degree temperature, the change of length divided by length should be a unit. That would be, then you would get an alpha is equal to 1. However, because this is not always true, in fact it is never true, L2 minus L1 is a very small amount for a 1 degree Kelvin. Therefore, alpha has to have very, very small values. And if you look around the table, you will find the linear expansivity is of orders of magnitudes of 10 to the minus 3, minus 4, depending on which material you take. Now, we earlier said in case of linear, because one would like to analyze it further, let's look at volumetric expansion. So now you have material which is in a cube shape, and it is now going to expand in all three directions, in the x direction, the y direction, and the z direction. So in other words, it's going to have now a volume change. Now the volume change is final volume minus the initial volume, V2 minus V1. Let's represent it as it is printed on the slide, which you can see on your screens, by delta V, where V2 is the volume after expansion and V1 is the original volume. Let's name the coefficient of volume expansion as beta, so as to not to confuse it with alpha, which is the coefficient of linear expansion. Just similarly, like we tried to analyze the relationships between linear expansion, let's look at the change in volume expansion. So the change in volume would depend upon the initial temperature or the change in temperature. The higher the change in temperature, the more the expansion. The smaller the change in temperature, the smaller the expansion would be. And the change in temperature should also be proportional to the original volume. If you have a larger volume, then of course the change would be larger. If you have a smaller volume, the change would of course will be smaller. Combining these two together, we find that the change in volume should be equal to the original volume multiplied by change in temperature, which gives us, when converted to an equation, that the change in volume should be equal to the coefficient of volumetric expansion multiplied by the original volume multiplied by the change in temperature. Rearranging, we can always find that V2, we get the increase, is what we are looking at, should be equal to the original length V1 multiplied by 1 plus beta, change in temperature, which is T2 minus T1, and beta, which is the coefficient of volumetric expansion, has to be V2 minus V1 divided by V1 multiplied by T2 minus T1. In other words, we have now relationships which tell us what to do this. Now, let's pose a question to you. On the slide, you have a figure which shows a nut. This is a normal nut with your nut and bolt systems, which you normally use. You can say this is used to hold the tires of a car, etc., etc. It has many uses. Now, the nut is made of metal. It's basically a nut is a metallic piece with a hole drilled inside it. My question to you is, when the nut is heated, it expands. Like we have said, made of a material which expands when heated. The question is, what happens to the size of the hole? A, does it expand? B, does it contract? Or C, does it remain the same? What I'm going to do is let you think over it. And in the course of this lesson, sometime later, I'm going to explain to you what exactly happens. So, food for thought for you. Think over it. You have a nut with a hole in it. The nut is heated, it expands. What happens to the hole? Does it remain the same? Does it contract? Or does it expand? Let us then continue with our discussions. Now, let us look at expansion of liquids, or for that matter, gases. Now, liquids, unfortunately, do not have a shape of their own. So when a liquid is heated, we know it should expand. But in order to study this expansion, we have to put the liquid in a container. Now, when you put a liquid in a container, the container also has some coefficient of expansion. It is also going to expand or contract depending whether we are heating it or we are cooling it. So when we are considering expansion of fluids are liquids and gases, we also have to take into consideration the expansion of the container. We know that liquids expand more than the solid. Now, container, of course, is made of solids. The liquid expansivity is more. So this causes a little slight alteration. Now, if I'm going to heat that liquid, I have to be careful where I heat it. or how it is heated. You see, if I am going to heat it from outside, from external sources, then the container is going to be heated first, and the liquid is going to be heated at a later stage, because heat has to travel from the source to the container to the liquid. So there is a two-step process, and the first step, of course, the container gets heated, so it expands first. That is why when we look at thermometers, liquid and glass thermometers, when we dip them in something which is at a higher temperature, the level of the mercury falls, or level of the alcohol. If you are using a alcohol thermometer, it is going to drop a little, and then it is going to start to rise. Very simply, when the thermometer was dipped in this liquid or into a hot, whatever temperature of which we are measuring, the bulb of the thermometer expands first, causing the liquid to drop a little, and then, of course, once the liquid gains that energy, starts expanding, heating, of course, then the expansion is linear, and that is what we record. However, on the other hand, if we have a container which contains a liquid and we heat it from the inside, like we do in electric kettles, then what's going to happen? Because the liquid is now in contact with the source, the liquid is going to get heated immediately, and the container is going to be heated at a later stage. Therefore, the liquid level is going to rise immediately, very simply because liquid expands more than the solid. Liquid is going to rise immediately. Now, once the container starts heating, it's going to expand. However, the liquid is going to expand more. Therefore, the level of the liquid is going to continuously rise, even though it starts to rise at a lower rate later on. And we can always look at it depending upon what material the container is made of. If it is made of material which has a very low rate of expansion, or the coefficient for linear or volumetric expansion is very low, then there is almost no change in the level of the rate of the rise of liquid. However, if it is made of material which has a high expensivity constant, then the level might change at a different rate. Now, when we're looking at such type of containers, we have to look at the real expansion of the liquid. Now, let's say a liquid was at temperature T, you went to temperature T2. For this difference in temperature, the liquid, let's say, expanded this much. However, the container expanded. So you have the real expansion is going to be the expansion of the liquid plus the expansion of the container. However, we can do with the expansion of the container, like I discussed earlier, we can eliminate or minimize the expansion of the container if we choose a liquid in such a way that its rate of expansion is very, very large as compared to the rate of expansion of the container. Or we force the liquid into a very fine capillary tube where its expansion rate is far, far greater than the expansion of the capillary. And there we can say within a given temperature range, within the appreciable range, it is going to behave as a linear expansion, just like we have in a thermometers and we do. Now, in the earlier part of my discussions, we said there are certain materials which do not expand like liquids or do not expand when heated. These materials are given a special name, and we say they are anomalous materials. In other words, they behave different from what is normal. Water, fortunately, is one such material. Why fortunately? We are going to discuss that as we go along. Water has got an anomalous expansion between 0 degrees and 4 degrees. So when water is heated from 0 degrees to 4 degrees, rather than expanding, it contracts. In other words, its density increases between that point, which has got very serious ramifications and which are very, very useful, and we utilize them, or in fact, nature has utilized this anomalous behavior of water to its benefit. Why is it said unusual? This is unusual or anomalous behavior because when you are cooling something, it contracts, but when water is cooled between 10 degrees and 0 degrees, it first contracts and then starts expanding, and therefore it is an anomalous behavior. Very few materials have such behavior. Now, what are the effects of such a behavior? How does it affect it? A, because material expands when it is being cooled, its density has to decrease because the mass is the same, it occupies now a larger volume, so it becomes denser, and therefore it rises. Therefore, once water converts into ice, it expands manifold, and therefore ice floats on water. This means that if you have a water body, then the temperature of the water body is going to fall down in winter. As the temperature goes down, the land mass, the temperature is going down. However, for the water mass, the temperature of the surface is going to fall down, but because the lower portion is at a higher density, its temperature will remain at 4 degrees centigrade for a very long period of time. Only very shallow lakes are the ones which freeze in winter. However, large aquatic bodies like large deep lakes or the oceans do not freeze total. Because they do not freeze totally, that means aquatic or marine life can move from the surface down underneath, and they can survive the winter. They do not need to freeze. The second effect of such an anomalous expansion is that when water expands when freezing or it's becoming cold, it causes cracks in mountains. Even mountains suffer that wrath because water vapor or rain might accumulate somewhere. When it freezes, it expands, and if the crack is of insufficient strength, it breaks them. In everyday life, in cold areas, we have pipes, water pipes, which are bursting in winter if they are not properly insulated. That is one of the things which we see when water behaves anomalously. Now let us look at expansion in gases. Now, just like liquids require a container for it to have shape, a body, similarly gases will also require a container to contain it. Unlike liquids, where the atoms and molecules are very close packed together, you cannot compress a liquid, you can still compress a gas. For example, you can take a syringe, and you can just push and pull the gas out. However, if we close the end of the syringe, like it is shown in your diagram, when you apply a pressure, what is going to happen is the plunger is going to go up to a certain extent, and then it stops. I have to apply a larger amount of force in order to make the plunger go further. Because I can make it go further by applying a larger force, that allows us to know that gases can be compressed. Because they can be compressed, we do not consider normal expansion as per se, like in liquids and solids. However, for expansion of gases, we use different relationships. The relationship which we are going to be looking today is for expansion of gases is going to be known as Boyle's law. Boyle's law states that for a mass of gas of volume V and pressure P, they are inversely proportional. In other words, V is proportional to 1 over P, or if you are going to remove it, we say remove the proportionality constant there, we get product of pressure and volume is a constant, which is the statement of Boyle's law, or PV is constant. Now, the PV graph is shown on your curve, and which it shows that as pressure is increased, the volume becomes smaller, or if volume is increased, the pressure becomes larger, and this is used in different aspects, and this is the way gases behave. Now, because PV is constant, it means P1 V1, if you have a gas with volume 1 and pressure V1, it should be a constant. Now, if you have the same gas at a different pressure, that is P2, and volume is V2, it's a constant. Because the constants are the same, you can equate the two equations and you get the general equation in which we are interested, that is P1 V1 is equal to P2 V2. So knowing the pressure, initial volume, knowing the final volume, we can find the final pressure. Knowing the final pressure, we can find the final volume. So this is an equation which is very, very useful to us to solve different problems. Now, in this case, the only thing which we have to be careful about is that there are two restrictions to Boyle's law. A, that the mass of the gas has to remain constant. The other, Boyle's law states that the temperature should not change. Now, when we say the temperature does not change, when we compress a gas, some heating effect does take place due to friction, due to compression of the molecules. So we have to wait for a certain period of time for that heat to be dissipated in order to satisfy Boyle's law. Boyle's law basically is very easy to verify. We take YouTube On one side we have a container with water, other side we have a tube which is sealed at the top, has the mass of air in it, and as we increase or decrease the height, the pressure is equal to rho gh, like we know, and as the pressure increases or decreases, the volume will also increase or decrease inversely. As you increase the pressure, the volume becomes less. You decrease the pressure, the volume becomes more. This is basically what Boyle's law is, and which you are looking at. Now, for the application of Boyle's law, let us do a numerical. We have a cylinder which contains 1500 centimeter cube of a gas at a pressure of 1.5 into 10 to the 5 pascals. Pascals being the unit of pressure, it is force per unit area, but we will not go into that. We just say that the unit of pressure is pascals. If the gas is compressed 250 centimeter cube, let us find the new pressure, assuming that the temperature has not changed. Because the temperature has not changed, A, that means we can apply Boyle's law. B, because we have not introduced any gas into the system, nor we have taken out any gas out of the system. Therefore, the mass, initial mass and the final mass of the gas is constant. That gives us the right to use Boyle's law or Boyle's relationship to get our question solved. The data which we have is P1 is equal to 1.5 into 10 to the 5 pascals. Pressure 2 is something which we have to find out. The initial volume was 1500 centimeter cube. The final volume is 250 centimeter cube. Putting them in the relationship P1 V1 is equal to P2 V2, we find 1.5 into 10 to the 5 multiplied by 1500 is equal to P2 into 250. Rearranging, we find out what the final pressure would be, and that is given on your slide. Now, gases can also behave in a different way. Like we said, that we have kept temperature constant, whereas another scientist by the name of Charles did a lot of work on gases, and he said that if we keep the volume of fixed mass of gas constant, in other words, we have a volume which is now constant, and we have a gas which we do not either take out or introduce more gas into it. Therefore, mass is constant, volume is constant. In this situation, it says that the temperature is directly proportional to the volume. So you increase the temperature, the volume is going to increase. You decrease the pressure, the volume is going to decrease. So fixed mass of gas, if you increase the temperature, the volume is going to rise. You decrease the temperature, the volume is going to be lesser. Charles' law plotted this and found the relationship to agree to a linear equation. So you have a straight line like it is shown in your graph. However, what we say is V by T, as you know as in Charles' law, the volume divided by temperature is a constant, or volume is proportional to temperature. Now, because volume is proportional to temperature, that means V1 divided by T1 is a constant, and V2 divided by T2 should also be constant. The constant is same in both cases, so we can equate them, and we say V1 divided by T1 is equal to V2 divided by T2. That means if you know the initial volume and you know the initial temperature, you can find, knowing one of the two quantities, the final volume or the final temperature, we can find the other. We can find either the final volume or the final temperature. Charles' law also has a further addition to it. Now, if we extrapolate, that means we have not experimentally got the data, but we have got the data up to a certain point, but we continue producing that line until it meets the x-axis, which is the temperature axis. We find that it meets at a temperature of 273 degrees Celsius, minus 273 degrees Celsius, is where this curve will cross the x-axis. It has a certain connotations, which we will discuss as we continue along. Now, the only thing which you have to be careful about, Charles' law and any gas laws, is that when you're looking at temperatures, we have to work in the Kelvin temperature. Why? As we go into the next slide, into the next portion of our lesson, we will find out why it is true. Now, there is a third law which governs the gases, which is known as the pressure law. It simply says that pressure for a fixed mass of any gas and its temperature are directly proportional to each other, provided the volume is kept constant. Now, if you have a constant volume, then as you increase the temperature, the pressure has to increase. Now, in other words, I have a container, the walls of which are solid. they cannot move. So if I increase the temperature inside the gas, the pressure within is going to increase. If I decrease the temperature, the pressure inside is going to be decreased. This is known as the pressure law, and it says P by T is a constant, so giving us P1 divided by T1 is equal to P2 divided by T2. And again, if you find it's a straight line, and the line will intercept also at minus 273 degrees Kelvin, which now gives us the concept of absolute zero. We just found that 273 degrees is a temperature, minus 273 degrees Celsius, is a temperature at which both Charles' law and pressure law ultimately return a value in which either the volume becomes zero or the pressure becomes zero. That is why physicists have named this temperature as absolute zero, that there can be no temperature below this, because if you go below this, the line is going to cross the x-axis and you're going to get either a negative volume or a negative pressure, which of course does not have a meaning in physics. Now, in order to understand this, let us look at an application of Charles' law. And application, of course, means solving a numerical. We have a volume of gas which is in a container containing about 2.5 meter cube of gas. What would be the volume this gas would occupy if its temperature is increased by a factor of 3? And the further question to it, sub-question, suggests a possible practical usage for this effect. The data which we have here is that T1 is equal to T Kelvin. We are not given the temperature, we are just given it's any temperature T. T2 has to be, of course, 3 times, so we just replace it by 3T. You can replace it by X, that does not really matter. V1 is 2.5 meter cube, and the volume 2 is something which we have required, again in meters cubed. The relationship which we have for Charles' law is V1 T1 is equal to V2 T2, giving us 2.5 divided by T should be equal to V2 divided by 3T. Cross multiplying, what we get is the volume 2 should be 2.5 multiplied by 3, giving us volume is 7.5 meter cube. Now the second part of the question, we have solved the volume part, that the volume is going to be increased 7.5 times. However, what practical usage we can put to it? The practical usage we normally have is in hot air balloons, when a burner heats up the gas to at least twice its original temperature, thus making it expand, and that is what provides the lift for the balloons in flight. Now, the 3 laws, the pressure law, Boyle's law, and Charles' law, can be combined into the Avogadro's law. Avogadro's law simply states that the pressure and the volume divided by the temperature is a constant, and which leads us to the ideal gas equation, which is PV is equal to nRT, where N and R, because they are both constants, it technically is the constant we are looking at, because when 2 constants are multiplied, the result is, of course, again a constant. Now, in this case, we say the V is the volume of the gas, T is the temperature of the gas, P is the pressure of the gas, N is the number of moles of the gas. That is the physical term. Actually, it means what is the mass of the gas we are looking at. And R is Rydberg's gas constant. You can always look it up in a table of constants and find out what its value is. Do remember, from now on, whenever we are going to be using gas equations, we are only going to be looking at the absolute scale or the Kelvin scale. So if you are given temperatures in Celsius or in Fahrenheit, you have to first convert them into Kelvin, and then only we can use them in the gas equation, because otherwise person is going to say the temperature of an object was 1 degree Celsius, I take it to 2 degrees Celsius, so the temperature has doubled, therefore the volume should double, because temperature and volume are directly proportional, which is not true. If the temperature is 273 degrees Kelvin, then you have to take it something like 546 degrees Kelvin for the volume to double. So that is where you have to be very, very careful. So in gas laws, you have to be particular that you have to convert temperature in the Kelvin scale, and you will get correct answers. You will not make a mistake. Now, when we say the PV is equal to nRT is the gas equation, this gas equation is for ideal gases. What is an ideal gas? An ideal gas is simply a gas which obeys the gas laws. It should obey the Boyle's law, it should obey the Charles law, it should obey the pressure law, and hence the Avogadro law or the gas equation. Do we have ideal gases in nature? Yes. we have gases which are approximately ideal. All noble gases are approximately ideal. They approximately correspond to the gas equation. However, when you're looking at diatomic or normal gases, they do not, and certain corrections have to be made to the gas equation. Now, I posed a question to you a little while back. We said you had a nut which had a hole in it. We had said that, and when you heat the nut, it expands. Now, what happens to the hole? Does the hole expand? Does the hole contract? Or does it not change? In order to make it simpler for you, let us take the same nut. Now have the top view of the nut for you on the slide. Let's take the nut. In B, I have filled the nut with a material which is the same material as the nut. Think over it. What will happen now? When I heat it, is the hole going to expand? Is it going to contract? Or is it going to remain the same? And we are going to continue with that. Now, let's look at a few questions to see what the different parts of this exercise which we have done with you over this period says. We said, what is the relationship between linear expansivity and volumetric expansivity? What are the relationships between the coefficients? Now, if you look at a linear expansion, the linear expansion is L plus delta L. However, if you look at volumetric expansion, each side of the volume, in other words, the length, the breadth, and the height, all three are going to expand, and you are going to get a change in volume, which is equal to L plus delta L cubed. So the volume change is going to be a cubic relationship. However, the relationship between the coefficients is normally 1:3. Why is it so? You can just ask your mathematics professor, who's going to be in a better position to explain to you why this is, because once you solve it mathematically, you do find that the coefficients are going to be in a relationship of 1:3. We are not going to go into that because that becomes beyond the scope of what we are trying to teach you. Now, you all must have seen different wires which are laid down electricity poles. They are given certain sag in summer. The question is, why are they given this sag in summer? Now, if you look at the fact, or if you appreciate the fact that in winter, the wires are going to contract. Now, if they're not given this sag, then in winter, if they contract, they're just going to make the poles collapse. And that is why some sag is given. So either the poles are going to collapse or the wire is going to snap, which can also be dangerous for us as we go along. So let us come back to the question of the metallic nut. What happens to the metallic nut when you heat it? Does the hole expand? Does it contract? Or does it remain the same? And in order to explain it, let's say that I take a bolt and I tie it inside the nut. The bolt and the nut are now made of the same material. Now, because the bolt and the nut are the same material, the bolt, when heated, expands. It can only expand if the hole had expanded. In other words, the hole has to expand. Now, how do we justify this? You have atoms which are equally spaced. So when you heat, the spacing between the atoms increases, and that is what increases the hole. It is not that because this is a nut, the inside has to go inside and the outside has to go outside. Therefore, the hole is either to contract or to become the same. No. As you heat, the hole has also to expand. We can do it another thing. We can also explain it in a different way. If you have a very thin ring and you heat it, what happens to that ring? That ring expands. In other words, the hole has expanded. You use it in order to put the hoop on a wooden wheel. When you have a wooden wheel, the hoop is always made slightly smaller. You heat it up, it expands, and then you put it on the wooden wheel, cool it, it contracts and keeps the wheel together. Another example is then when you have a glass bottle with a metallic cap on it and it's jammed. You can't open it. So what do? You ask your ladies in the house, and they will tell you that we will put it under warm water. The warm water flows on the cap expands, and the hole, of course, expands, and you can then unscrew it, and the bottle becomes simple. So when you heat it, the hole expands. That is the answer to the question which we have discussed. In today's lecture, what we have looked at is, we looked at thermal expansion. We said that all solids, liquids, and gases expand when heated. Solids expand by a certain amount, liquids expand slightly more, and gases expand even more. However, for the solid, we had the coefficient of linear expansivity, the coefficient of volumetric expansivity. Solids, because they retain their own material, their own volume, therefore we just had to look at it as an individual case. However, in the case of liquids and gases, you require a container in which you have to keep that liquid in order to maintain its shape. Therefore, when liquids were expanding, we had to look at the expansion of the liquid as well as the expansion of the container. For gases, we looked at the gas equations, which was the Boyle's law, which said PV is equal to constant. We looked at the temperature law, which says temperature is proportional directly to the volume. We looked at the pressure law. Temperature law was, of course, Charles's law. We looked at the pressure law, which said pressure is directly proportional to temperature. Combining these three equations, we came into the Avogadro law and hence the gas equation. And the gas equation basically is the generalized equation of all three. Because if you remember, in Boyle's law, we said we are keeping temperature and mass of gas is constant. If we see PV is equal to nRT, then R, N, NT are kept constant. So PV is constant. That's Boyle's law. If you keep volume constant, you keep N constant, you keep R constants, then P is proportional to T, which is the pressure law, and similarly for the volume law. And I think that should be enough for today. Word for thought. Let's meet next time and we'll see. Thank you very much.